All right. So in case you're actually looking in the textbook, we're in chapters 16 through 17 here. We're only covering a small fraction of chapter 17 when we do the acid-base titration, which will be about 2 weeks from now. Okay. I'm going to start out with this slide. This was not specifically in the reading, but you might have inferred it. Acid-base chemistry is all about two ions. It's about the hydrogen ion, which is also known as the hydronium ion. And that is going to tell you if you've got a lot of if you've got a lot of hydronium or if you've got a lot of hydrogen ions, you've got an acid. The more of those ions that you've got, the stronger that your acid is. The hydroxide ion, on the other hand, is going to determine basicity. If you've got a lot of hydroxide ions compared to the hydronium ion, then you've got a base. And we're always doing this comparing the two things to each other. The one other thing to indicate here that's really important is that because we're talking about chemistry with ions, both acids and bases conduct electricity. The more ions they have in solution, the better they conduct electricity. So you can have some acids that are very strong electrolytes. They'll conduct electricity strongly. And you'll have some acids that are very weak electrolytes. They conduct electricity weakly. It's got to do with the concentration of the hydronium ion that will affect that for acids. For bases, it's the hydroxide ion. Okay. So the next slide here has properties of acids and properties of bases on it. I combined both onto one slide here. Okay, acids such as citric acid, notice the little picture, they're going to contain at least one hydrogen atom in them. Their properties are that they have a sour taste and that they react with active metals to produce hydrogen gas. They don't react with non-reactive metals because non-reactive metals don't react, okay? Hence the name. As a state of fact, vinegar owes its taste to acetic acid. Okay, citrus fruits contain citric acid. Yeah, lemon bars. All right. Bases. Bases taste bitter as long as they're not poisonous. Okay. If they're poisonous, you shouldn't taste them. Right? Okay. Bases, in theory, bases taste bitter. So before you die of poisoning, you would taste bitter. I'm not going to do that. All right. So bases also feel slippery. Hence, many soaps contain bases. Okay. So Arrhenius says that we have to produce hydronium or hydrogen in order for it to be an acid. So Arrhenius is focusing right here. He's focusing on the result of what happens when an acid is placed in water. He also goes on to state that a base is going to be this part here. And he focuses on the fact that a base produces hydroxide ions. Bronsted defines an acid as a proton donor, so you actually have to look at the chemical reaction and you have to go, hey, this thing is actually going to lose this proton here when it gets to the other side of the reaction. So I'm going to label this thing as my acid. On the other hand, he's going to also note that this thing, NH3, when it gets to this side of the reaction, winds up having an extra hydrogen. So it is accepting it. So who's got the more thorough definition? Who's got the definition that looks more in depth? Bronsted. Okay, so whose definition works more often? Bronsted. Okay. Arrhenius' definition only works for aqueous solutions. He's from Denmark. They have different letters. Notice here that we can label an acid as turning into a conjugate base on the right-hand side, and that the base turns into a conjugate acid on the right-hand side. So there are bases and their conjugate acids. There are acids and their conjugate bases. So you guys are going to be responsible for being able to identify those things. Conjugate just means that it is what formed from the original acid. Okay, conjugates are always on the right-hand side of the reaction. What formed from the original acid. So an acid always forms a conjugate base because it's got less hydrogens. And a base always forms a conjugate acid because the conjugate will have an extra hydrogen. Okay. All right. So conjugates consist of two substances that are related to each other by donating and accepting a single proton, right? That's what we just said on that last slide. What would their conjugate base be? So if I've got the acid HClO, what would the conjugate base be? All right, according to Bronsted, what does an acid do? What does an acid do?
Oh, it's ClO.
All right, it loses a hydrogen ion, right? So this would become ClO, but it loses a hydrogen ion, so it has to become negatively charged because a hydrogen ion is H+. So if it loses its H+, it becomes ClO negative. Okay. What about this guy over here, the H2PO4 ion? Right, HPO4 with a 2 negative charge. So the charge changes, and also the number of hydrogens change. Notice an acid always donates a proton, so it's only going to be one of the protons. How about hydronium? What's it going to form for its conjugate base? Careful. It was positive, right? If it loses a positive charge, it becomes neutral. You got to remember about the zero. It's important. And then check out this one. Usually acids are clearly marked with the hydrogen out front, so you know. In this particular case, I think I'd take the hydrogen off the ends. So I would write it like this. Yeah, the charge becomes no charge. Yep. Here. There's one more slide after this. Okay. Can these be conjugate acid-base pairs? First off, can H2O being an acid be H3O as its conjugate? Can H2O be the acid that forms the conjugate base H3O? All right, H3O could be the acid, and then this could be the conjugate base, but not in the direction that this says. It wants the acid base. Okay. Right? C, can this be an acid and this be the conjugate base? Let's look at C first. Can C do it?
Yes. Yes.
Yeah. Okay. C cannot, because the definition of an acid is it loses how many protons? 1. What did C do? It lost 2, so C is not a good answer either. Okay. How about B? B, they don't even make sense, right? Where'd the nitrate go? Where'd the nitrogen go? Or where did it appear from? Finally, D. Can D be an acid conjugate base pair?
Yes.
Yes, it lost 1 hydrogen and became negative.